hypothesis test about proportions. Okay, so I'll go over this sort of in general, and then we'll get into some specific examples. And start with kind of the sort of the terminology. This diagram shows 4 possible outcomes of testing the null hypothesis, which is usually denoted H0, versus the alternative, which is HA. HA would usually be what we're trying to prove. For example, if you're trying to prove that a new drug is better than the old drug or has a higher cure rate than the old drug, H0 would be the new drug is not better than the old drug, and the alternative would be HA would be the new drug is better than the old drug. And so when we're setting up hypotheses, either H0 or H0 is going to be true, or HA will be true. Sometimes it's called H1. Some books use H1, or some books use HA, but the alternative could be expressed either way. And also either we don't reject H0 or we reject H0. So altogether there's 4 possibilities. H0 could be true and we don't reject H0. H0 could be true and we reject H0. HA could be true and we don't reject H0. HA could be true and we reject H0. Two of these are errors. If we reject H0 and H0 is true, that's called a type 1 error. If we don't reject H0 and HA is true, that's called a type 2 error. The probability of a type 1 error is denoted by the Greek letter alpha, which is a little bit like an A, sort of between an A and an X, but it looks a little bit like an A, a little bit like an X. But and then the type 2 error is denoted by the Greek letter beta. And then 1 minus alpha is called our confidence level. I like to call alpha the level of doubt, but it's usually called the level of significance. 1 minus alpha is our confidence level, and 1 minus beta, it'd be our it's called the power of the test. So 1 minus alpha and 1 minus beta would both be probabilities of drawing a correct conclusion. In practice, usually we don't know beta, or we don't know 1 minus beta. And we'll get into, I'll say a little bit more about that a little bit later. Yeah, alpha level of significance. Actually, it's the maximum desired level of doubt. The p-value, which is actually computed based on our data, is the actual level of doubt, or the computed level of doubt. And alpha, we compare it to alpha, which is the maximum desired level of doubt. Yeah, in order to compute beta and 1 minus beta, you have to pick a specific value of the population parameter. Okay, so we'll be working with some formulas, and we'll also be working with some. We're going to use trees for small samples. I'll get into some specific examples in a little bit. For the larger samples, if n p0 and n times 1 minus p0 are both bigger than or equal to 10, you can use these formulas here. If HA has a not equal to symbol, you want to use this first formula. If HA has a less than symbol, you want to use the second formula. If HA has a greater than symbol, you want to use the this third formula here. Typically the null hypothesis will have an equal sign in it, and HA will have one of these symbols in it, not equal to, less than, or greater than. And that's the reason we can compute alpha but not beta. In order to compute beta, we need a specific alternative here. But typically we do have a specific number for the null hypothesis, and that enables us to compute alpha. Okay. Okay, and then so these formulas are for computing a p-value. You can also, for small samples, we use a tree to compute a p-value. And then when you have your p-value, usually we want to compare it to 0.05. Usually we want at least moderate evidence. P-value between 0.01 and 0.05 is moderate evidence, so that's going to be our usual standard to decide whether or not we reject the null hypothesis. Depending on the situation, there might be some situations where you want strong evidence. You want a p-value of less than 0.01. But anyway, this graph here, or this chart here, kind of gives you some adjectives to interpret a p-value. So p-value between 0.1 and 1, little or no evidence. P-value between 0.05 and 0.1, some evidence. Between 0.01 and 0.05, moderate evidence. Between 0.001 and 0.01, strong evidence. Between 0 and 0.001, very strong evidence. So the p-value is always going to be between 0 and 1. And there's also a standard error is kind of part of this formula here. Actually, if you bring the n down to the denominator, that will give you the standard error. And this expression here, p hat minus p0 times square root of n over square root of p0, 1 minus p0, that's called this test statistic. For some of the tests, I put the p0 first, but if you're just computing the test statistic, you need the p hat first. Okay, so the formula for standard error, if you're going to compute the standard error separately, it's part of the formula for the p-value, but if you want to compute it separately, this is the formula there, and it represents the standard deviation of the sample proportion. So square root of p0 times 1 minus p0 over n. p0 is the value of p under the null hypothesis. And the test statistic, the p hat always comes first before the p0 if you're computing the test statistics separately. P hat minus p0 and then times square root of n over square root of p0 times 1 minus p0. If you've already computed the standard error, then you can just do p hat minus p0 divided by the standard error. So it's the z-score for the sample proportion. Generally, a test statistic of more than 2 or less than -2 indicates at least moderate evidence against H0. Okay, so let's get into specific examples, because I think it's a little hard to talk about this in the abstract. It's easier to talk about in terms of specific examples. So here's example 1. In a random sample of n equal 1 patient, the proportion cured by a new drug, p hat, 1 out of 1. So there's only one patient. That patient was cured. I want to compare it to the 0.47 cure rate of the old drug. And we want confidence level of 95% or 0.95, and that means the level of doubt of 0.05. In symbols, we want to test H0, p equals 0.47. New drug is not better than the old, versus the alternative, HA, p is greater than 0.47. New drug is better than the old. So this is called a right-tailed test. For this small sample, we're not actually going to use a formula, but if we were using the formula, that would be the third formula for the right-tailed test. The first step is to check whether n times p0 and n times 1 minus p0 are both at least 10. So in fact, they're not. N is only 1. Our sample size is 1. P0 is the value of p if H0 is true. That's the cure rate of the old drug. 1 1 times 0.47 is 0.47, which is not bigger than 10. And 1 minus p0 is 0.53. 1 times 0.53 is 0.53, which is also not bigger than 10. So that means we have to use an exact method, such as a tree. So this tree is not going to have a lot of paths because we only have, our sample size is 1. So either the patient is cured or is not cured. And there's a 0.47 chance of being cured, 0.53 chance of not being cured. So our p-value is going to be the 0.47. This is the probability of getting a p-hat this big if H naught was true. So if H naught was true, even if the new drug is no better than the old, we still have a 47% chance of getting a patient that was cured. So our p-value is 0.47, and if this is more than 0.5, so the p-values are level of doubt, and usually we want at least moderate evidence. So we want a p-value of less than 0.05, and this is not. So that means we fail to reject H naught. Sample does not provide enough evidence to say that the new drug is better. The one patient was cured. It was a perfect cure rate, but it could have happened by chance. We never, technically you should never accept H naught. Sometimes you'll see in textbooks where they're accepting H naught, and the reason they do that is that the language is a little bit awkward to say we fail to reject H naught because you have a double negative. But the reason it's better to say we fail to reject H naught is that it might be a bigger sample would provide stronger evidence. In this sample, all of the patients, there's only one patient, and that patient was cured. So that was a perfect cure rate. But the problem was the sample size was not big enough, so we really need a bigger sample to be convinced that the new drug is better than the old drug. So we don't really accept H naught. Accepting H naught means that the new drug is no better than the old, but we're just saying, basically we're saying we don't know. We don't, the sample did not provide enough evidence. We can also compare the p-value to this chart here. Usually we want at least moderate evidence, but we get our p-value of 0.47 is between 0.1 and 1, so that more specifically there's little or no evidence that the new drug is better. Okay, so let's try a somewhat bigger sample here. So this sample here, we have a sample of 2 patients. The proportion cured p-hat 1 out of 2, or 0.5, and we want to compare this to the 0.47 proportion cured by the old drug. Again, with 95% confidence, 5% doubt. Hypotheses are still the same. Null hypothesis, p equal 0.47, new drug is no better than the old, versus the alternative, p is greater than 0.47, new drug is better than the old. And then we can check n times p0, 2 times 0.47, 0.94 is not bigger than 10, n times 1 minus p0, 1.06, not bigger than 10. So we have to use an exact method such as a tree. Okay, so this tree is going to have be a little bit more involved because we have 2 patients. First patient is either cured or not. And the second patient is also either cured or not. And each patient has a 0.47 chance of being cured. if H naught is true, if the new drug is no better than the old, each patient has a 0.47 chance of being cured, 0.53 chance of not being cured. 1 minus 0.47 is 0.53. Okay, so we're sort of interested in the paths where at least one of the two were cured, because that's our p-hat. Our p-hat was 1 out of 2, and we want our p-value is the probability of getting a p-hat this big or bigger if H naught is true. And as you go along the paths of the tree, you want to multiply. So it's 0.47 times 0.47. 0.47 times 0.47, 0.2209, and that would be cured. They're both cured. And then we have 0.47 times 0.53. That's 0.2491. That's cured. First one is cured, second one not. And then we have 0.53 times 0.47. That will be the same. 491. That's not cured, then cured. And then we don't really need this bottom path here, because we're only looking at the paths where at least one of the two was cured. So on the bottom path, neither patient was cured. So if we add these up, the total will be our p-value. That's 0.7191. So that's our p-value. So that's not, our p-hat was of 0.50. 0.5 was actually a little bit bigger than, a little bit better than the old drug. 0.47, a little bit higher cure rate, but that could have happened by chance. It was not much bigger, and it was a small sample. In a small sample, it could very well have happened by chance. So our p-value, 0.7179. Again, it's bigger than alpha, and we failed to reject it. Sample does not provide enough evidence, and it's also bigger than 0.1. If we compare it to this chart here, 0.7 is bigger than 0.1. It's little or no evidence. Okay, so let's make this a bigger sample. Again, the issue here was not so much we didn't really prove that the new drug was not better. We just we had a small sample size. So let's see what happens with a bigger sample. We have in example 3, we have a sample of n equal 200 patients. Proportion cured by new drug p-hat 200 divided by 120 divided by 200, which is 0.6. And we want to compare it to the 0.47 proportion cured by the old drug. Again, we want 95% confidence and 5% doubt. Now, not all researchers use 95% confidence. That's probably the most commonly used level of confidence, but some of them, like 99%, would also be fairly common. You could also use 97% or some other 90%. It's a little bit arbitrary. It's up to the researcher. And then some researchers just report the p-value. They don't even decide ahead of time on a level of confidence. Okay, so the same set of hypotheses. We're testing H naught, p equal 0.47, new drug is no better than the old, versus HA, p is greater than 0.47, new drug is better than the old. And the first step, we want to check if n times p0 is at least 10. 200 times 0.47, 94, that's bigger than 10, that's a yes. N times 1 minus p0, 200 times 0.53 is 106, that's also bigger than 10. So that means we can use normal approximation. We don't need to rely on the trees. In fact, the tree would not be practical here. A tree would have probably millions of paths here. Each time you add a new patient, the number of paths doubles. So doubling doesn't sound like it's a huge problem, but the numbers get bigger, faster than you might think. So, you know, with 2 patients, you have 4 paths, 3 patients, 8 paths, 4 patients, 16 paths, 5 patients, 32 paths. By the time you get up to 10 patients, already you're over 1,000 paths. Okay, so we can use the formulas, and we're using a right-tailed test because we have a greater than symbol in HA. We're testing whether the new drug is better than the old. Oftentimes, when you're testing a new drug, you're not really interested in whether it's worse than the old drug, so you use a right-tailed test for HA, and so that means we can. This is the formula here, and so we want probability z less than p0 is 0.6, p hat 0.47, n is 200, and 1 minus p0 is 0.53, 1 minus 0.47, 0.53. So this is the probability z less than, and I'll put these in a calculator. 0.6 minus 0.47 equals times second square root 200 equals divided by second square root 0.47 times 0.53 equals. We get approximately 3.68. And that's going to, oh, you know what, I need a negative, so it'll be negative. Because, yeah, for this test, we want to do 0.47 minus 0.6. So we want the P0 first. That'll be so you want to look in row negative 3.6 and column 8 of our table, of the Z table, and that'll give a p-value of 0.0001. Okay. So that's our p-value. So that provides very strong evidence that the new drug is better. It's less than alpha, it's less than our desired maximum level of Dow alpha. So we reject H0 with 95% confidence and conclude the cure rate of the new drug is higher than that of the old. And also, if we compare it to our chart here, we have 3 zeros after the decimal point. So it's less than 0.001. The sample provides very strong evidence. Again, this was a right-tailed test. If we were doing a two-sided test, we would multiply the p-value by 2 for a two-sided test. You see a 2 in the formula here. If it's a left-tailed test, the p-hat comes first before the p0. Yeah, it's a right-tailed test because we're trying to prove that the new drug is better than the old. And we can compute some parts of this formula separately. This p-hat minus p0, if you bring the n down to the bottom, you have p0 times 1 minus p0 over n, and the square root of that whole thing. That's called the standard error. So we could, sometimes it's useful to compute that separately. The standard error here, p0 is 0.47, 1 minus p0 0.53, and sample size is 200. So that's second square root 0.47 times 0.53 divided by 200. 0.035, approximately 0.035. 291642. Okay, I'm going to store that in memory. Okay, so so generally the if the sample proportion is more than 2 standard deviations from the null proportion, then then the sample provides at least moderate evidence. So if we go 2 standard deviations above the null proportion, the value of p, if h naught is true, is 0.47. If we add 2 standard deviations to it, we get 0.54, which was less than p hat. So our p hat is more than 2 standard deviations above p0. So it's another indication that our sample provides at least moderate evidence. We can also compute the z-score for our sample proportion. For the z-score, going back to these formulas again, you notice that for the left-tailed test, p hat comes first. For the right-tailed test, p0 comes first in the formula. But if you're computing the test statistics separately, you want to put the p hat first. So p hat is 0.6, p0 is 0.47, and we already computed the standard error here. It's 0.035291642. So if we do that computation, 0.6 minus 0.47 equals, divided by second recall, approximately 3.68. And generally, if the z-score is more, or your test statistic is more than 2 or less than -2, that indicates at least moderate evidence against h naught. For a right-tailed test, you want it more than +2. For a left-tailed test, you want it less than -2 to reject h naught. If for a two-sided test, it would be either or. You could have either more than 2 or less than -2. Okay, so I think that's it for example 3, and then we can do example 4. Okay, so I want to sort of go over some of the terminology here. I mentioned that at the beginning, some of the terminology, but I would like to go over it in the context of a particular example. So in this example here, we can have a random sample of n equal 200 patients determine the cure rate of a new drug, whether it's higher than the 0.47% cure rate of the old drug. So we're testing h naught, p equal 0.47, new drug is no better than the old, versus HA, p is greater than 0.47, new drug is better than the old. And we want to state whether and what type of error and give symbols for the probabilities. So if we conclude that the new drug is better when it is not, that would be an error. We conclude the new drug is better when it's not. So that means we're rejecting h naught. So if we conclude the new drug is better, that means we reject h naught. And when it's not better, if it's not better, that means h naught is true. So if we reject h naught when h naught is true, that is a type 1 error. Its probability is alpha. That's called the level of significance. I like to call it the level of doubt. So that's the anyway. That's the answer to part A. Okay, part B, we conclude new drug is better, and that means reject h naught. When it is, that means HA is true. Okay, when it is include the new drug, so that would not be an error. So that means we reject h naught when HA is true. It's not an error. That's 1 minus beta. That's the power of the test. Part C, we fail to conclude the new drug is better when it is not. So fail to conclude that means we don't reject H naught, fail to reject, don't reject. When it's not, that means H naught is true. Okay, so that that's going to be this top path here. We don't reject H naught when H naught is true. So that's 1 minus alpha. That's the confidence level, and that's not an error. Okay. And then part D. Don't reject H naught. Fail to conclude the new route is better. That means we don't reject. And when it is better, that means HA is true. So that means that would be a type 2 error, and its probability is beta. Don't reject H naught when HA is true. That's a type 2 error. So I put the answers down here at the bottom. So that's part A, type 1 error, which is represented by alpha or the p-value. Part B, the power of the test, it's 1 minus beta, not an error. Part C, confidence level, 1 minus alpha, not an error. Part D, type 2 error, that's represented by beta. And that concludes this presentation.